What if the universe you think you know is just the tip of the iceberg? What if the rules of space and time as we understand them are completely rewritten by something so mysterious, so powerful, that it defies imagination? Welcome to the enigmatic world of black holes, cosmic phenomena that challenge everything we thought we knew about reality. These aren't just empty voids in space. They're cosmic monsters with gravitational pulls so intense that not even light can escape their grasp. But here's the kicker: black holes aren't just destructive. They're also the universe's ultimate puzzle pieces, holding secrets that could reshape our understanding of existence itself. In this video, we're diving into 30 mind-blowing facts about black holes that will completely change how you see the universe. From the bizarre to the downright terrifying, get ready to have your mind stretched, twisted, and maybe even spaghettified. So buckle up, because by the end of this journey, the universe might not look the same to you ever again. Let's get started. Now, turning to our first fact, let's shatter a common misconception. Black holes are not empty. Far from it. These cosmic giants are some of the densest objects in the universe, packing an unimaginable amount of mass into a tiny space. Imagine taking the entire Earth and compressing it down to the size of a marble. That's the kind of density we're talking about. This extreme concentration of mass creates a gravitational pull so strong that nothing, not even light, can escape once it crosses a certain point. That's why they're called black holes, because they trap light, making them invisible to our eyes. But their density doesn't just create gravity, it warps the very fabric of space-time itself. Picture space-time as a stretched-out sheet. A black hole is like placing a bowling ball on that sheet, causing it to bend and distort everything around it. This warping is what makes black holes so fascinating and so terrifying. They're not just cosmic vacuums, they're the universe's ultimate heavyweights, bending reality as we know it. Now, turning to our second fact, let's dive into one of the most defining features of a black hole, the event horizon. Think of the event horizon as the ultimate point of no return. It's the boundary around a black hole where the gravitational pull becomes so intense that not even light, the fastest thing in the universe, can escape. Once something crosses this invisible line, it's gone forever. No turning back, no second chances. This is why the event horizon is often called the edge of a black hole. It's not a physical surface you can touch or see. It's more like a one-way door into the unknown. To visualize this, imagine a river flowing toward a waterfall. The event horizon is like the edge of that waterfall. Once you go over, there's no way to climb back up. For a black hole, the waterfall is the immense gravity pulling everything inward, and the edge is the event horizon. Light, which usually zips through space at incredible speeds, gets caught in this gravitational current and can't break free. This is why black holes appear black. They trap light, making them invisible to our eyes. But the event horizon isn't just a boundary. It's also a key to understanding how black holes interact with the universe around them. It's the point where the rules of physics as we know them start to break down, where space and time become so warped that our everyday understanding of reality no longer applies. It's a place where the universe shows us just how strange and mysterious it can truly be. And as we move forward, we'll explore even more mind-bending phenomena that black holes have to offer. Now, turning to our third fact, let's explore one of the most bizarre and fascinating effects of black holes: spaghettification. Yes, you heard that right, spaghettification. It's the process where objects, including unlucky astronauts, get stretched into long, thin strands, much like a piece of spaghetti. This happens because of the extreme tidal forces near a black hole. Imagine you're falling feet first into a black hole. The gravitational pull on your feet would be much stronger than the pull on your head, simply because your feet are closer to the black hole. This difference in gravity creates a stretching effect, pulling you apart like taffy. Your body would be stretched thinner and thinner until, well, you'd resemble a cosmic noodle. It's not exactly a pleasant thought, but it's a vivid way to understand just how intense the forces around a black hole can be, and here's where it gets even weirder. As you're being stretched, you'd also start to compress sideways. So while you're being pulled into a long, thin strand, you'd also be squeezed from the sides like a tube of toothpaste being flattened. It's a double whammy of cosmic proportions. Now you might be wondering, could you survive this? The short answer is no. Spaghettification is as final as it sounds. But it's also a reminder of just how extreme and unforgiving the universe can be. Black holes don't just bend the rules of physics, they completely rewrite them. And as we continue, we'll uncover even more mind-bending facts about these cosmic enigmas. Now turning to our fourth fact, let's dive into the realm of supermassive black holes. These cosmic giants are not your average black holes, they're millions or even billions of times more massive than our Sun. To put that into perspective, imagine squeezing millions of suns into a single point. That's the kind of mind-boggling density we're talking about here. Supermassive black holes are often found at the very heart of galaxies, including our own Milky Way. In fact, at the center of our galaxy lies a supermassive black hole known as Sagittarius, a star. But don't worry, it's about 26,000 light-years away, so it's not something we need to lose sleep over. These colossal black holes play a crucial role in shaping the galaxies they inhabit. Their immense gravitational pull influences the motion of stars, gas, and even entire star systems around them. Think of them as the anchors of galaxies, holding everything together while also driving the formation of new stars and structures. But here's something even more fascinating. Supermassive black holes can also power some of the brightest objects in the universe, like quasars. When matter falls into these black holes, it heats up and emits enormous amounts of energy, lighting up the cosmos in ways that can be seen from billions of light-years away. So, while black holes might seem like destructive forces, supermassive black holes are also cosmic architects, shaping the very fabric of the universe. And as we continue, we'll uncover even more about how these giants influence the cosmos in ways we're only beginning to understand. Now turning to our fifth fact, let's explore the fascinating world of stellar black holes. Unlike their supermassive cousins, stellar black holes are born from the dramatic deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. This leads to a catastrophic collapse, triggering a massive explosion known as a supernova. During a supernova, the outer layers of the star are blasted into space while the core collapses inward. If the core is massive enough, typically more than 3 times the mass of the Sun, it crushes down into an infinitely dense point, forming a stellar black hole. These black holes are smaller in size compared to supermassive ones, but don't let their size fool you. Their gravitational pull is still incredibly strong, capable of bending light and warping space-time around them. Stellar black holes are scattered throughout galaxies, often lurking in the remnants of their explosive births. While they may not have the same colossal scale as supermassive black holes, they are no less intriguing. In fact, their formation gives us a glimpse into the life cycles of stars and the incredible forces at play in the universe. So, the next time you look up at the night sky, remember that some of those twinkling stars may one day end their lives in a blaze of glory, leaving behind a stellar black hole as their final legacy. And as we move forward, we'll uncover even more about these cosmic wonders and the secrets they hold. Now turning to our sixth fact, let's dive into the mysterious realm of primordial black holes. Unlike stellar or supermassive black holes, primordial black holes are thought to have formed not from collapsing stars, but in the chaotic moments just after the Big Bang. Imagine the early universe, a hot, dense soup of energy and matter. In some regions, the density of this cosmic soup could have been so extreme that it collapsed under its own gravity, forming tiny black holes. These are the primordial black holes, and they could be as small as an atom or as massive as a star. What makes primordial black holes so intriguing is their potential connection to dark matter. Scientists have long been puzzled by dark matter, the invisible substance that makes up most of the matter in the universe. While we can't see it directly, we know it's there because of its gravitational effects on galaxies and galaxy clusters. Some researchers believe that primordial black holes could be a key piece of the dark matter puzzle. If they exist in large numbers, they might account for some or even all of the dark matter we observe. But how do we find something so elusive? Scientists are searching for primordial black holes using a variety of methods. One approach involves looking for their gravitational effects on light from distant stars, a phenomenon known as microlensing. Another method involves detecting the tiny bursts of radiation that might be emitted if a primordial black hole evaporates, as predicted by Stephen Hawking's theory of Hawking radiation. While no definitive evidence has been found yet, the hunt continues, and every discovery, or lack thereof, brings us closer to understanding these enigmatic objects. Primordial black holes remind us that the universe is full of mysteries waiting to be uncovered. They challenge our understanding of the cosmos and push the boundaries of what we know about the early universe and the nature of dark matter. As we move forward, we'll explore even more mind-bending facts about black holes and the secrets they hold. Now turning to our seventh fact, let's explore one of the most groundbreaking ideas in modern physics, Hawking radiation. Proposed by the legendary physicist Stephen Hawking, this theory suggests that black holes aren't completely black after all. Instead, they emit a faint form of radiation, which means they can slowly lose energy and over time evaporate entirely. But how does this work? Imagine the edge of a black hole right at the event horizon. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence and then annihilate each other. Normally, this happens without any noticeable effect, but near a black hole, something extraordinary can occur. One of these particles might fall into the black hole while the other escapes into space. The escaping particle carries away a tiny bit of the black hole's energy, and over billions or even trillions of years, this process can cause the black hole to shrink and eventually disappear. This phenomenon has huge implications for the lifespan of black holes. While stellar and supermassive black holes are incredibly long-lived, Hawking radiation means they aren't eternal. Smaller black holes, like hypothetical primordial ones, would evaporate much faster, potentially ending their existence in a burst of energy. This also raises fascinating questions about what happens to all the information that falls into a black hole, a puzzle known as the black hole information paradox. Hawking radiation challenges our understanding of black holes and the universe itself. It bridges the gap between quantum mechanics and general relativity, two of the most fundamental but seemingly incompatible theories in physics. As we continue to unravel the mysteries of black holes, Hawking's work reminds us that even the darkest corners of the cosmos hold secrets waiting to be discovered. Now turning to our eighth fact, let's dive into one of the most mind-bending effects of black holes, time dilation. Near a black hole, the immense gravitational pull doesn't just warp space, it warps time itself. This means that time passes slower the closer you get to a black hole compared to someone far away from its influence. Imagine two astronauts. One is orbiting close to a black hole, while the other is observing from a safe distance. For the astronaut near the black hole, time would appear to move normally, but for the observer far away, the astronaut near the black hole would seem to move in slow motion. If the astronaut spent a few hours near the black hole, years or even decades could pass for the observer back home. This isn't science fiction, it's a real consequence of Einstein's theory of general relativity. This effect becomes even more extreme as you approach the event horizon, the point of no return. If someone were to fall into a black hole, an outside observer would never actually see them cross the event horizon. Instead, they'd appear to freeze in time, slowly fading from view as the light from them becomes increasingly redshifted. Meanwhile, for the person falling in, time would feel normal, but the universe outside would appear to speed up dramatically. Time dilation near black holes isn't just a fascinating thought experiment. It has real implications for our understanding of the universe. It shows how gravity doesn't just shape space, but also the very fabric of time. This phenomenon has been observed in less extreme forms, like with satellites orbiting Earth, which experience slightly slower time compared to us on the surface. But near a black hole, the effect is so powerful that it challenges our perception of reality itself. As we continue to explore the mysteries of black holes, time dilation reminds us that the universe is far stranger and more wondrous than we can imagine. And with that, let's move forward to our next fact, where we'll uncover how black holes can spin and what that means for the cosmos. Now turning to our ninth fact, let's explore another fascinating feature of black holes, their ability to spin. Unlike stationary objects, black holes can rotate, and this rotation creates a region around them known as the ergosphere. The ergosphere is a unique zone where space-time itself is dragged along with the black hole's spin, a phenomenon called frame dragging. This means that nothing, not even light, can remain stationary in this region. Everything is forced to move in the direction of the black hole's rotation. The faster a black hole spins, the more pronounced this effect becomes. In fact, the ergosphere can extend beyond the event horizon, creating a sort of twisted space-time bubble around the black hole. Matter and energy that enter the ergosphere can gain energy from the black hole's rotation, a process that could theoretically be harnessed to extract energy from the black hole itself. This idea, known as the Penrose process, is still theoretical but highlights just how dynamic and powerful spinning black holes can be. The spin of a black hole also affects the behavior of matter in its vicinity. As material falls toward the black hole, it forms a swirling disk called an accretion disk. The rotation of the black hole can cause this disk to heat up and emit intense radiation, making spinning black holes some of the brightest objects in the universe. Additionally, the spin can influence the direction and intensity of the jets of particles that are often ejected from the poles of black holes, which can stretch across thousands of light years. Spinning black holes are not just cosmic curiosities, they play a crucial role in shaping the universe around them. From powering quasars to influencing the structure of galaxies, their rotation is a key factor in understanding how black holes interact with their surroundings. And as we continue to study these enigmatic objects, their spin reminds us that black holes are not just static voids but dynamic engines driving some of the most energetic processes in the cosmos. With that, let's move forward to our next fact, where we'll uncover how black holes can collide and merge, releasing waves that ripple through the fabric of space-time. Now turning to our 10th fact, let's dive into one of the most dramatic events in the universe, black hole mergers. When two black holes come close enough to each other, their immense gravitational pull can cause them to spiral inward, eventually colliding and merging into a single, more massive black hole. This cosmic dance is not just a spectacle, it's a cataclysmic event that releases an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself. These gravitational waves were first predicted by Albert Einstein over 100 years ago, but it wasn't until 2015 that scientists made the groundbreaking detection using the Laser Interferometer Gravitational Wave Observatory, or LIGO. This discovery confirmed Einstein's theory and opened up a whole new way of observing the universe. Unlike light, which can be blocked or distorted, gravitational waves travel through everything, giving us a clear signal of these violent cosmic events. When black holes merge, the energy released is staggering. In fact, for a brief moment, the energy output can outshine all the stars in the observable universe combined. This energy is carried away by the gravitational waves, which stretch and compress space-time as they pass through it. The detection of these waves has allowed scientists to study black holes in ways that were previously impossible, providing insights into their masses, spins, and even the environments in which they form. The significance of black hole mergers goes beyond just understanding these mysterious objects. They also help us test the limits of our current understanding of physics, particularly in extreme conditions where gravity is at its strongest. Each merger event is like a cosmic laboratory, offering clues about the nature of space, time, and the fundamental laws that govern the universe. As we continue to detect more black hole mergers, we're not just witnessing the birth of new black holes, we're also piecing together the story of how these objects shape the cosmos. From their role in galaxy formation to their influence on the evolution of the universe, black hole mergers are a key piece of the puzzle in our quest to understand the universe. With that, let's move forward to our next fact, where we'll explore the fascinating connection between black holes and the strange world of quantum mechanics. Now turning to our 11th fact, let's venture into the mind-bending intersection of black holes and quantum mechanics. At first glance, these two realms seem worlds apart. Black holes, with their immense gravitational pull, belong to the domain of general relativity, while quantum mechanics governs the behavior of the smallest particles in the universe. Yet, when these two theories collide, they create some of the most profound mysteries in modern physics. One of the biggest puzzles is the black hole information paradox. According to quantum mechanics, information about the state of a system can never be completely destroyed, but black holes with their event horizons seem to defy this rule. When matter falls into a black hole, it's thought to be lost forever, leaving no trace of the information it once carried. This contradiction has sparked heated debates among physicists for decades. Is the information truly gone, or is it somehow preserved in a way we don't yet understand? Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, which could carry away some information. However, this radiation is random and doesn't seem to encode the specifics of what fell into the black hole. This has led to theories like the holographic principle, which suggests that all the information about the matter swallowed by a black hole might be encoded on its surface like a cosmic hologram. If true, this would mean that black holes aren't just simple voids but incredibly complex systems storing vast amounts of information. The debate over the information paradox isn't just an academic exercise, it's a battle for the soul of physics. Resolving this paradox could help us unify general relativity and quantum mechanics, two of the most successful but incompatible theories in science. It could also reshape our understanding of space, time, and the very nature of reality. As scientists continue to explore this frontier, black holes remain at the center of some of the most exciting and challenging questions in physics. They force us to rethink our assumptions and push the boundaries of what we know. With that, let's move forward to our next fact, where we'll uncover another surprising feature of black holes, the idea that they might have something called hair. Now turning to our 12th fact, let's dive into the quirky idea that black holes might have hair. No, we're not talking about cosmic barbershops. This is about the no-hair theorem, a concept in physics that suggests black holes are incredibly simple objects. According to this theorem, black holes can be described by just three properties: their mass, their electric charge, and their spin. Everything else about the matter that falls into a black hole, its shape, color, or composition, is lost forever. In other words, black holes are bald with no hair to distinguish them. But here's where things get interesting. Recent research has hinted that black holes might not be as bald as we once thought. Some scientists believe that black holes could retain faint traces of the matter they consume, like a kind of quantum hair. This hair wouldn't be visible in the traditional sense, but it could encode subtle information about what fell into the black hole. Think of it as a cosmic fingerprint, a way for black holes to keep a record of their past meals. This idea challenges the no-hair theorem and opens up new possibilities for solving the black hole information paradox. If black holes do have hair, it could mean that information isn't lost forever, it's just hidden in ways we're only beginning to understand. And while the concept of black hole hair might sound funny, it's a serious area of study that could reshape our understanding of these mysterious objects. So the next time you picture a black hole, don't imagine it as a smooth, featureless void. Instead, think of it as a cosmic detective, quietly holding onto clues about the universe's secrets. With that, let's move forward to our next fact, where we'll explore how black holes power some of the brightest objects in the universe, quasars. Now turning to our 13th fact, let's explore how black holes power some of the most dazzling objects in the cosmos, quasars. These celestial powerhouses are among the brightest things in the universe, outshining entire galaxies. But what exactly makes them glow so intensely? The answer lies in the incredible energy released by the accretion of matter around supermassive black holes. When a black hole pulls in gas, dust, and other material from its surroundings, this matter doesn't just vanish into the void. Instead, it forms a swirling disk around the black hole, known as an accretion disk. As the material spirals inward, it heats up to extreme temperatures, reaching millions of degrees. This process generates an enormous amount of energy, which is released as light, X-rays, and other forms of radiation. The result, a quasar, a beacon of light so powerful it can be seen from billions of light years away. Quasars are not just bright, they are also incredibly active. The energy they emit can influence the formation of stars and even shape the evolution of entire galaxies. In fact, many astronomers believe that quasars played a crucial role in the early universe, helping to light up the cosmos during a time when galaxies were still forming. So, the next time you hear about a quasar, remember that it's not just a distant point of light. It's a testament to the incredible power of black holes, transforming the chaos of falling matter into some of the most brilliant phenomena in the universe. With that, let's move forward to our next fact, where we'll uncover how black holes can be invisible, yet still leave their mark on the cosmos. Now turning to our 14th fact, let's dive into one of the most intriguing aspects of black holes, their invisibility. Black holes are, by their very nature, invisible. Why? Because their gravitational pull is so strong that not even light can escape them. Without light, there's nothing for our eyes or telescopes to detect. But just because we can't see them directly doesn't mean they're not there. In fact, their presence can be inferred through the dramatic effects they have on the space and matter around them. Take, for example, the supermassive black hole at the center of the M87 galaxy. While we can't see the black hole itself, we can observe the shadow it casts. This shadow is created by the black hole's event horizon, the point beyond which nothing can escape. Light from the surrounding gas and dust bends around the black hole, creating a dark silhouette against the glowing material. This shadow was famously captured in the first ever image of a black hole, released in 2019, giving us a glimpse of the invisible. But the shadow isn't the only clue. Black holes also reveal themselves through the way they influence nearby stars and gas. Stars orbiting close to a black hole move at incredible speeds, their paths warped by the black hole's immense gravity. Gas and dust spiraling into a black hole heat up and emit X-rays, which we can detect even from millions of light years away. These indirect observations allow scientists to map the presence of black holes across the universe, even though they remain hidden from direct view. So, while black holes may be invisible, their impact on the cosmos is anything but. They shape galaxies, warp light, and leave behind clues that help us unravel the mysteries of the universe. With that, let's move forward to our next fact, where we'll explore the fascinating idea that black holes might create shortcuts through space and time. Now turning to our 15th fact, let's explore one of the most mind-bending ideas in astrophysics, the possibility that black holes could create wormholes. Imagine a tunnel through space and time, a shortcut that could connect two distant points in the universe in an instant. This is the concept of a wormhole, and while it sounds like something straight out of science fiction, it's rooted in the equations of Einstein's theory of general relativity. According to these equations, a wormhole could theoretically form if a black hole's intense gravity warps space-time so dramatically that it creates a bridge to another region of the universe, or even another universe entirely. This bridge, often called an Einstein-Rosen bridge, would act like a cosmic shortcut, allowing matter, or even a spacecraft, to travel vast distances in a fraction of the time it would normally take. But before you start packing your bags for an interstellar adventure, there's a catch. Wormholes, if they exist, are incredibly unstable. The moment they form, they would likely collapse under their own gravity unless held open by some form of exotic matter with negative energy. This kind of matter has never been observed, and its existence remains purely theoretical. Even if wormholes could be stabilized, navigating one would be fraught with challenges, from extreme tidal forces to the risk of the wormhole collapsing mid-journey. Despite these hurdles, the idea of wormholes continues to captivate scientists and science fiction writers alike. They've become a staple of stories about time travel and interstellar exploration, offering a tantalizing glimpse of what might be possible if we could master the secrets of space-time. While we're far from proving their existence, the study of wormholes pushes the boundaries of our understanding of physics and inspires us to dream of the incredible possibilities hidden within the fabric of the universe. With that, let's move forward to our next fact, where we'll delve into the speculative idea that black holes might be gateways to other universes or dimensions. Now turning to our 16th fact, let's dive into one of the most speculative and fascinating ideas in modern cosmology: the possibility that black holes could serve as gateways to other universes or dimensions. This concept takes the idea of wormholes a step further, suggesting that black holes might not just connect distant points in our universe, but could also open pathways to entirely different realities. The idea stems from the complex mathematics of general relativity and quantum mechanics, which hint that the extreme conditions inside a black hole could create a bridge to another universe. Some theories propose that the singularity at the center of a black hole, a point of infinite density, might not be the end of space and time as we know it, but rather a doorway to a new realm. This could mean that our universe is just one of many in a vast multiverse, with black holes acting as the cosmic portals between them. However, it's important to note that these theories are highly speculative. While the math suggests such possibilities, there's no direct evidence to prove that black holes lead to other universes. The concept of a multiverse itself is still a topic of intense debate among scientists, with some arguing that it's a natural extension of our understanding of physics, while others see it as more of a philosophical idea than a scientific one. What makes this idea so intriguing is how it challenges our understanding of reality. If black holes truly are gateways to other dimensions, it would mean that the universe is far more complex and interconnected than we ever imagined. It also raises profound questions about the nature of existence itself. Could there be other versions of us in these parallel universes? What laws of physics govern those realms? And if we could somehow travel through a black hole, what would we find on the other side? While these questions remain unanswered, the exploration of black holes and their potential connection to the multiverse continues to push the boundaries of science. It's a reminder that the universe is full of mysteries waiting to be uncovered, and that even the most outlandish ideas can inspire us to think bigger and dream bolder. With that, let's move forward to our next fact, where we'll explore another mind-bending aspect of black holes, their powerful magnetic fields. Now turning to our 17th fact, let's explore another fascinating feature of black holes, their magnetic fields. While we often think of black holes as purely gravitational monsters, some of them also possess incredibly powerful magnetic fields. These fields are generated by the swirling, superheated gas and plasma that surround the black hole, particularly in its accretion disk. As this material spirals inward, it creates electric currents, which in turn produce magnetic fields that can be billions of times stronger than those found on Earth. These magnetic fields play a crucial role in shaping the behavior of matter around the black hole. One of the most dramatic effects is the formation of relativistic jets, narrow beams of particles that shoot out from the black hole's poles at nearly the speed of light. These jets can stretch for thousands or even millions of light years, making them some of the most energetic phenomena in the universe. The magnetic fields help channel and accelerate the particles, acting like cosmic particle accelerators. Without these fields, the jets wouldn't be nearly as powerful or focused. But the influence of magnetic fields doesn't stop there. They also affect how matter falls into the black hole, creating turbulence and shaping the structure of the accretion disk. In some cases, magnetic fields can even slow down the rate at which a black hole consumes matter, effectively regulating its growth. This interplay between gravity and magnetism is a key area of study for astrophysicists, as it helps us understand not just black holes, but also the behavior of other cosmic objects like neutron stars and active galactic nuclei. What's truly remarkable is how these magnetic fields challenge our traditional view of black holes as simple, featureless voids. Instead, they reveal a dynamic and complex environment where multiple forces are at play. This complexity makes black holes even more intriguing as they continue to defy our expectations and deepen our understanding of the universe. With that, let's move forward to our next fact, where we'll uncover how black holes can be detected through the X-rays they emit. Now turning to our 18th fact, let's dive into how black holes can be detected through the X-rays they emit. While black holes themselves are invisible, the hot gas swirling around them in their accretion disks emits a tremendous amount of energy, including X-rays. This gas, heated to millions of degrees as it spirals inward, glows brightly in the X-ray part of the electromagnetic spectrum, giving astronomers a way to see these otherwise hidden cosmic giants. To detect these X-rays, scientists use specialized telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton. These instruments are designed to capture high-energy X-ray emissions from space, allowing researchers to study the behavior of matter as it approaches a black hole. By analyzing the intensity and patterns of these X-rays, astronomers can determine the presence of a black hole, estimate its size, and even study the dynamics of its accretion disk. One of the most fascinating aspects of this detection method is how it reveals the extreme conditions near a black hole. The X-rays are produced by particles moving at nearly the speed of light, colliding and releasing energy in the form of high-frequency radiation. This process not only helps us locate black holes, but also provides insights into their feeding habits, such as how quickly they consume matter and how their accretion disks are structured. What's truly remarkable is how this technology has transformed our understanding of the universe. Before X-ray telescopes, many black holes remained hidden, their presence only inferred through their gravitational effects. Now, thanks to these advanced instruments, we can observe black holes directly through the X-rays they produce, opening up a new window into the most extreme environments in the cosmos. With that, let's move forward to our next fact, where we'll explore how black holes can have companions in the vastness of space. Now turning to our 19th fact, let's explore how black holes can have companions in the vastness of space. In the cosmic dance of the universe, black holes are not always solitary. They often exist in binary systems where they orbit another massive object, such as a star or even another black hole. These pairings are not just fascinating to imagine, they're also incredibly valuable for scientists studying the behavior and properties of black holes. In a black hole star binary system, the black hole's immense gravity pulls material from its companion star, creating a swirling accretion disk around the black hole. As this material spirals inward, it heats up and emits radiation, including X-rays, which we discussed earlier. This process allows astronomers to observe the black hole indirectly, even though it remains invisible. By studying the light and energy emitted from these systems, researchers can measure the black hole's mass, spin, and even its feeding rate. But it gets even more intriguing when two black holes orbit each other. These black hole binaries are some of the most extreme objects in the universe. As they spiral closer together, they emit ripples in space-time known as gravitational waves, which were first detected in 2015 by the LIGO Observatory. These waves provide a wealth of information about the black holes, including their masses, distances, and how they merge. The collision of two black holes is one of the most energetic events in the cosmos, releasing more energy in an instant than all the stars in the universe combined. These binary systems are like cosmic laboratories, offering scientists a unique opportunity to test theories about gravity, space-time, and the behavior of matter under extreme conditions. They also help us understand how black holes form and evolve over time. For instance, studying black hole star pairs can reveal how black holes grow by consuming their companions, while black hole binaries shed light on how these massive objects come together in the first place. What's truly remarkable is how these systems challenge our understanding of the universe. They show us that black holes are not just isolated anomalies but active participants in the cosmic ecosystem, interacting with other objects in ways that shape the fabric of space and time. With that, let's move forward to our next fact, where we'll delve into the theoretical concept of naked singularities, black holes without event horizons. Now turning to our 20th fact, let's dive into the intriguing and somewhat mysterious concept of naked singularities. Unlike the black holes we've discussed so far, which are hidden behind their event horizons, naked singularities are theoretical black holes that lack this defining boundary. In other words, they are singularities, points of infinite density, that are exposed to the universe with no event horizon to shield them from view. The idea of naked singularities challenges one of the fundamental principles of general relativity, which suggests that singularities should always be hidden behind event horizons. This principle, known as the cosmic censorship conjecture, was proposed by physicist Roger Penrose to preserve the predictability of the universe. If singularities were exposed, their extreme gravitational effects could create unpredictable and chaotic conditions, making it impossible to apply the laws of physics as we know them. So why do scientists even consider the possibility of naked singularities? The answer lies in the extreme conditions of the early universe and certain mathematical solutions to Einstein's equations of general relativity. In these scenarios, it's theorized that under specific conditions such as rapid rotation or asymmetrical collapse, a singularity could form without an event horizon. This would make it naked, allowing its intense gravitational effects to influence the surrounding space-time directly. The implications of naked singularities are profound. If they exist, they could provide a unique window into the nature of singularities and the extreme physics that govern them. They might also help us bridge the gap between general relativity and quantum mechanics, two theories that currently don't align. However, despite their theoretical appeal, naked singularities remain purely hypothetical. No observational evidence has been found to support their existence, and many physicists believe that nature might prevent them from forming, in line with the cosmic censorship conjecture. What makes this concept so fascinating is how it pushes the boundaries of our understanding. It forces us to question the limits of our current theories and imagine what might lie beyond them. As we continue to explore the mysteries of black holes, the search for naked singularities, or the proof that they cannot exist, remains one of the most exciting challenges in modern physics. With that, let's move forward to our next fact, where we'll explore how black holes can warp light, creating some of the most stunning visual phenomena in the universe. Now turning to our 21st fact, let's explore one of the most visually stunning effects of black holes, their ability to warp light. This phenomenon, known as gravitational lensing, occurs when the immense gravitational pull of a black hole bends the path of light traveling from objects behind it. Imagine a massive cosmic magnifying glass, but instead of simply enlarging an image, it distorts and multiplies it in fascinating ways. Here's how it works. When light from a distant star or galaxy passes near a black hole, the black hole's gravity acts like a lens, curving the light around it. This bending can create multiple images of the same object, or even stretch and twist the light into arcs or rings. These distorted images are not just beautiful, they are also incredibly useful for astronomers. By studying these lensed images, scientists can map the distribution of matter around the black hole and even measure its mass with remarkable precision. One of the most famous examples of gravitational lensing is the Einstein cross, a quasar whose light is bent by a galaxy in front of it, creating 4 distinct images arranged in a cross-like pattern. While this example involves a galaxy rather than a black hole, the principle is the same. Black holes, with their extreme gravity, can produce even more dramatic effects, sometimes magnifying distant objects that would otherwise be too faint to observe. Gravitational lensing isn't just a cosmic curiosity, it's a powerful tool for exploring the universe. It allows us to peer deeper into space than ever before, revealing galaxies and phenomena that would otherwise remain hidden. It also provides a unique way to test Einstein's theory of general relativity, confirming that even in the most extreme environments, his predictions hold true. So, the next time you see an image of a distant galaxy warped into a ring or arc, remember, you're witnessing the incredible power of a black hole to bend the very fabric of space-time. With that, let's move forward to our next fact, where we'll uncover the glowing rings of matter that surround some black holes, known as accretion disks. Now turning to our 22nd fact, let's dive into the glowing rings of matter that surround some black holes, known as accretion disks. These mesmerizing structures are not just beautiful to look at, they're also key to understanding how black holes behave and interact with their surroundings. An accretion disk forms when a black hole pulls in material from a nearby star or gas cloud. As this material spirals toward the black hole, it doesn't fall straight in. Instead, it orbits around the black hole, gradually losing energy and heating up due to friction and gravitational forces. This process creates a flat, rotating disk of superheated gas and dust that glows brightly, often in X-rays or other high-energy wavelengths. The intense heat and radiation from these disks make them some of the brightest objects in the universe. In fact, the light emitted by an accretion disk can outshine entire galaxies, making them visible across vast cosmic distances. But these disks aren't just cosmic light shows, they're also crucial for understanding black hole dynamics. By studying the properties of accretion disks, scientists can learn about the black hole's spin, mass, and even the rate at which it's consuming matter. One of the most fascinating aspects of accretion disks is their role in powering some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei. These disks can also produce powerful jets of particles that shoot out from the black hole's poles at nearly the speed of light. These jets can extend for thousands of light years and have a profound impact on their surrounding environments, shaping galaxies and influencing star formation. So, the next time you see an image of a glowing ring around a black hole, remember, you're looking at a cosmic engine, a swirling vortex of matter and energy that reveals the secrets of one of the universe's most mysterious objects. With that, let's move forward to our next fact, where we'll explore the quieter side of black holes, those that don't emit much radiation and are harder to detect. Now turning to our 23rd fact, let's explore the quieter side of black holes, those that don't emit much radiation and are harder to detect. While we often think of black holes as cosmic powerhouses, glowing with the energy of their accretion disks or blasting out jets of particles, not all black holes are so active. In fact, many black holes are dormant, quietly lurking in space without much fanfare. These quiet black holes, often referred to as inactive or dormant black holes, don't have a steady stream of matter falling into them. Without an accretion disk to heat up and emit light, they remain dark and nearly invisible. This makes them incredibly challenging to detect, as they don't produce the telltale X-rays or other high-energy signals that active black holes do. Instead, scientists have to rely on indirect methods to find them, such as observing the gravitational effects they have on nearby stars or gas clouds. One of the most famous examples of a quiet black hole is the one at the center of our own Milky Way galaxy, known as Sagittarius A star. While it occasionally flares up when it consumes a passing star or gas cloud, most of the time it's relatively quiet, emitting very little radiation. This makes it a fascinating subject of study, as it provides a glimpse into the behavior of black holes when they're not actively feeding. Despite their quiet nature, these dormant black holes are still incredibly important to study. They help scientists understand the full range of black hole behavior, from the most energetic to the most subdued. They also play a crucial role in the evolution of galaxies, as their gravitational influence can shape the movement of stars and gas over billions of years. Plus, studying quiet black holes can give us insights into how black holes form and grow over time, even when they're not actively consuming matter. So, while they may not be as flashy as their active counterparts, quiet black holes are just as fascinating and just as important to our understanding of the universe. With that, let's move forward to our next fact, where we'll explore just how widespread black holes are across the cosmos. Now turning to our 24th fact, let's dive into just how widespread black holes are across the universe. From the smallest stellar black holes to the colossal supermassive ones at the hearts of galaxies, black holes are everywhere, and they play a crucial role in shaping the cosmos as we know it. Stellar black holes formed from the collapse of massive stars are scattered throughout galaxies. These smaller black holes, though still incredibly dense and powerful, are just the tip of the iceberg. Then there are the supermassive black holes, which can weigh millions or even billions of times more than our Sun. These giants reside at the centers of most, if not all, galaxies, including our own Milky Way. Their immense gravitational pull influences the motion of stars, gas, and even entire galaxies, acting as cosmic anchors that hold galaxies together. But black holes aren't just confined to the centers of galaxies. Intermediate mass black holes, which are larger than stellar black holes but smaller than supermassive ones, have also been discovered in star clusters and other regions of space. These mid-sized black holes are thought to be the building blocks of their supermassive counterparts, growing over time as they merge with other black holes or consume matter. What's truly remarkable is how black holes, despite their mysterious and often invisible nature, are woven into the fabric of the universe. They're not rare anomalies, they're fundamental to the structure and evolution of galaxies. Without black holes, galaxies might not have formed in the way we see them today. Their gravitational influence helps regulate star formation, shapes the orbits of stars, and even drives the movement of gas and dust across vast cosmic distances. So, whether they're quietly lurking in the outskirts of a galaxy or reigning supreme at its center, black holes are everywhere, and they're shaping the universe in ways we're only beginning to understand. With that, let's move forward to our next fact, where we'll explore how black holes might hold the key to understanding the very origins of the universe itself. Now turning to our 25th fact, let's explore how black holes might hold the key to understanding the very origins of the universe itself. Black holes, with their extreme gravitational forces and mysterious nature, are not just fascinating objects in their own right, they also offer us a unique window into the early moments of the cosmos, including the Big Bang. When we study black holes, we're essentially peering back in time. The conditions near a black hole's event horizon, where gravity is so intense that it warps space and time, mimic some of the extreme environments that existed just after the Big Bang. By observing how matter and energy behave near black holes, scientists can gain insights into the high-energy processes that shaped the universe in its infancy. One of the most intriguing connections between black holes and the Big Bang lies in the concept of singularities. At the heart of a black hole lies a singularity, a point where gravity becomes infinite and the laws of physics as we know them break down. Interestingly, the Big Bang itself is thought to have started from a singularity, a point of infinite density and temperature. By studying black hole singularities, researchers hope to uncover clues about the conditions that existed at the very beginning of the universe. Additionally, black holes play a crucial role in cosmology by helping us understand the distribution of matter and energy in the universe. The way black holes interact with their surroundings, from swallowing stars to merging with other black holes, provides valuable data about the large-scale structure of the cosmos. These interactions can reveal how galaxies formed and evolved over billions of years, offering a glimpse into the universe's history. Moreover, the study of black holes has led to groundbreaking discoveries in physics, such as the detection of gravitational waves. These ripples in space-time caused by the collision of black holes carry information about the universe's most violent events. By analyzing these waves, scientists can test theories about the early universe and refine our understanding of the Big Bang. In essence, black holes are more than just cosmic vacuum cleaners, they're time capsules that preserve the secrets of the universe's birth. By unraveling their mysteries, we move closer to answering some of the most profound questions in science. How did the universe begin? What were its initial conditions? And how did it evolve into the vast, complex cosmos we see today? With that, let's move forward to our next fact, where we'll delve into the fascinating possibility of planets orbiting black holes. Now turning to our 26th fact, let's dive into the intriguing idea of planets orbiting black holes, a concept that sounds like it's straight out of science fiction, but might actually have some scientific merit. Imagine a world where the night sky is dominated not by a star, but by the eerie glow of an accretion disk swirling around a black hole. It's a fascinating thought, but could such a scenario really exist? The short answer is it's possible, but incredibly challenging. For a planet to orbit a black hole, it would need to be at just the right distance, far enough to avoid being torn apart by the black hole's immense gravitational pull, but close enough to remain gravitationally bound. This delicate balance would place the planet in what's known as a stable orbit, similar to how Earth orbits the Sun. However, the environment around a black hole is far more hostile than anything in our solar system. One of the biggest challenges for such a planet would be the lack of a traditional energy source. Planets in our solar system rely on the sun's light and heat to sustain life, but a black hole doesn't emit light in the same way. Instead, the planet would have to rely on the faint radiation emitted by the black hole's accretion disk, a swirling ring of superheated gas and dust. While this radiation could provide some energy, it would likely be insufficient to support life as we know it. Another major hurdle is the intense gravitational forces near a black hole. Even if a planet managed to maintain a stable orbit, it would be subjected to extreme tidal forces that could stretch and compress its surface, potentially triggering constant earthquakes and volcanic activity. Additionally, the planet would be bombarded by high-energy particles and radiation from the black hole's jets, making it an incredibly harsh environment. Despite these challenges, scientists have theorized that such planets could exist, especially around supermassive black holes at the centers of galaxies. In fact, some researchers have even proposed that these planets could form from the debris left over after a star is torn apart by a black hole's gravity. While this remains speculative, it opens up exciting possibilities for future discoveries. So, while the idea of planets orbiting black holes might seem like something out of a movie, it's not entirely beyond the realm of possibility. It's a reminder of just how strange and wondrous the universe can be. With that, let's move forward to our next fact, where we'll explore the mind-bending concept of using black holes for time travel. Now turning to our 27th fact, let's explore one of the most mind-bending ideas in all of science, the possibility of using black holes for time travel. This concept, while sounding like pure science fiction, actually has roots in the equations of Albert Einstein's theory of general relativity. According to some solutions to these equations, black holes could, in theory, create pathways through space and time that might allow for time travel. But how exactly would this work, and is it even remotely possible? The idea hinges on something called a closed time-like curve, a theoretical loop in space-time that could allow an object or person to travel back to their own past. Near a black hole, the extreme warping of space-time could, under certain conditions, create such a curve. If you were to enter this curve, you might theoretically emerge at a point in time before you even entered the black hole. It's a fascinating concept, but one that comes with enormous scientific hurdles. First, let's talk about the challenges. For starters, the conditions required to create a closed time-like curve are incredibly specific and would likely only exist near a rotating black hole known as a Kerr black hole. Even then, the process would require navigating the black hole's intense gravitational forces without being torn apart or crushed, a feat that's far beyond our current technological capabilities. Additionally, the energy required to manipulate space-time in this way is unimaginably vast, making it a purely theoretical exercise for now. Another major issue is the concept of causality, or the relationship between cause and effect. If time travel were possible, it could lead to paradoxes such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence. These paradoxes challenge our understanding of physics and raise questions about whether the universe would even allow such scenarios to occur. Despite these challenges, the idea of black holes as gateways to time travel continues to captivate scientists and science fiction enthusiasts alike. While it remains speculative, the concept pushes the boundaries of our understanding of space, time, and the fundamental laws of physics. It's a reminder that the universe is full of mysteries waiting to be unraveled. So, while we may not be hopping into a black hole to visit the past anytime soon, the theoretical possibilities are enough to spark endless curiosity and imagination. With that, let's move forward to our next fact, where we'll dive into how scientists use supercomputers to simulate black holes and unlock their secrets. Now turning to our 28th fact, let's explore how scientists use supercomputers to simulate black holes and unlock their secrets. These simulations are not just for fun, they're powerful tools that help us understand the behavior of black holes in ways that real-world observation simply can't. By recreating the extreme conditions around black holes in a virtual environment, researchers can test theories, make predictions, and even uncover new phenomena that might otherwise remain hidden. So, how do these simulations work? Imagine feeding the equations of general relativity into a supercomputer, along with data about a black hole's mass, spin, and surrounding environment. The computer then calculates how space-time bends, how matter behaves as it falls into the black hole, and even how gravitational waves ripple outward from a collision. These simulations are incredibly detailed, often taking weeks or even months to complete, but the results are worth it. They allow scientists to see what happens in regions of space that are otherwise impossible to observe directly. One of the most exciting applications of these simulations is in the study of black hole mergers. When two black holes collide, they create ripples in space-time called gravitational waves. By simulating these events, scientists can compare their predictions to real-world observations made by instruments like LIGO and Virgo. This not only confirms the accuracy of Einstein's theories, but also helps refine our understanding of how black holes behave under extreme conditions. Simulations also play a crucial role in exploring the mysteries of black hole interiors. For example, what happens to matter once it crosses the event horizon? While we can't observe this directly, simulations allow us to model the journey of matter as it spirals inward, giving us clues about the nature of singularities and the fabric of space-time itself. But perhaps the most important aspect of these simulations is their ability to test new ideas. From the behavior of accretion disks to the formation of jets, simulations provide a sandbox for scientists to experiment with theories and push the boundaries of our knowledge. They've even helped us understand phenomena like Hawking radiation and the potential for black holes to evaporate over time. In short, black hole simulations are like a window into the unknown, offering insights that would be impossible to gain through observation alone. They remind us that even in the realm of the unimaginable, science finds a way to explore, question, and discover. With that, let's move forward to our next fact, where we'll delve into how black holes are helping us bridge the gap between general relativity and quantum mechanics. Now turning to our 29th fact, let's dive into how black holes are helping us tackle one of the biggest mysteries in physics, the quest for a theory of quantum gravity. Black holes sit at the crossroads of two fundamental theories: general relativity, which describes the universe on a large scale, and quantum mechanics, which governs the behavior of particles on the smallest scales. The problem: these two theories don't play well together. General relativity breaks down when we try to apply it to the tiny, chaotic world inside a black hole, while quantum mechanics struggles to explain the immense gravitational forces at work. This is where black holes become the ultimate testing ground. At the heart of a black hole lies a singularity, a point where gravity becomes infinite and the laws of physics as we know them cease to function. To understand what happens here, scientists need a theory that unifies general relativity and quantum mechanics. This is the goal of quantum gravity, and black holes are the perfect laboratory for testing these ideas. For example, Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation, was a groundbreaking moment because it suggested that quantum effects could influence black holes. This discovery hinted at a deeper connection between gravity and quantum mechanics, sparking decades of research. One of the biggest challenges in this field is the so-called information paradox. According to quantum mechanics, information about particles can never be destroyed. But when matter falls into a black hole, it seems to vanish forever, leaving no trace. This contradiction has led to heated debates and fascinating theories, such as the idea that information might be encoded on the surface of the event horizon or even radiated away through Hawking radiation. Solving this paradox could be the key to unlocking the secrets of quantum gravity. Another area of exploration is the concept of quantum foam, a theoretical idea that suggests space-time is not smooth but instead made up of tiny, fluctuating bubbles at the smallest scales. Black holes, with their extreme gravitational fields, could provide clues about whether this foam exists and how it behaves. Simulations and mathematical models are helping scientists explore these ideas, but the answers remain elusive. Despite the challenges, the study of black holes and quantum gravity has already led to exciting breakthroughs. For instance, the holographic principle suggests that all the information about a three-dimensional space could be encoded on a two-dimensional surface, like the event horizon of a black hole. This idea has profound implications for our understanding of space, time, and the nature of reality itself. In short, black holes are more than just cosmic curiosities. They're the key to solving one of the greatest puzzles in physics. By studying them, we're not just learning about the universe, we're rewriting the rules of science itself. With that, let's move forward to our final fact, where we'll explore the ultimate fate of black holes and what it means for the universe as a whole. Now turning to our final fact, let's explore the surprising truth that black holes are not eternal. Despite their reputation as cosmic vacuum cleaners that devour everything in their path, black holes can actually evaporate over time. This mind-blowing phenomenon is thanks to something called Hawking radiation, named after the legendary physicist Stephen Hawking, who first proposed the idea. Here's how it works. At the edge of a black hole's event horizon, pairs of particles and antiparticles constantly pop into existence. Normally, these pairs annihilate each other almost instantly. But near a black hole, one particle can fall in while the other escapes, carrying away a tiny bit of the black hole's energy. Over unimaginably long periods of time, this process causes the black hole to lose mass and eventually evaporate completely. But don't expect this to happen anytime soon. For a typical stellar black hole, the process would take trillions upon trillions of years, far longer than the current age of the universe. However, for smaller black holes like the hypothetical primordial ones, evaporation could happen much faster, potentially ending in a spectacular burst of energy. So, what does this mean for the ultimate fate of black holes and the universe? If Hawking radiation is correct, black holes won't last forever. Over time, even the supermassive black holes at the centers of galaxies will fade away, leaving behind only faint traces of their once dominant presence. This raises fascinating questions about the long-term future of the cosmos. Will the universe eventually become a cold, dark expanse, devoid of stars, galaxies, and black holes? Or will new structures and phenomena emerge from the ashes of the old? While we don't have all the answers yet, the study of black holes continues to push the boundaries of our understanding. From their mysterious interiors to their eventual evaporation, black holes remind us that the universe is full of surprises and that even the most seemingly permanent things can change. And with that, we've reached the end of our journey through 30 mind-blowing facts about black holes, from their formation to their role in shaping galaxies, and from their bizarre effects on time and space to their ultimate fate. Black holes have proven to be some of the most fascinating and mysterious objects in the cosmos. So, what do you think? Did these facts change how you see the universe? Let us know in the comments below, and don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Thanks for watching, and until next time, keep exploring the wonders of the universe. Now turning to our conclusion, let's take a moment to reflect on the incredible journey we've just taken through 30 mind-blowing facts about black holes. From their unimaginable density to their ability to warp time and space, black holes have shown us just how strange and awe-inspiring the universe can be. We've explored how they form, how they grow, and even how they might one day disappear. Each fact has peeled back another layer of mystery, revealing just how much we still have to learn about these cosmic enigmas. Black holes challenge our understanding of the universe in ways that no other objects can. They force us to rethink the very nature of reality, from the way gravity works to the limits of space and time. They remind us that the universe is far more complex and unpredictable than we often imagine. And yet, with every discovery, we come a little closer to unraveling their secrets. So, what other mysteries do black holes hold? Could they be gateways to other dimensions or keys to understanding the origins of the universe itself? The answers are still out there, waiting to be discovered, and that's the beauty of science. It's a never-ending journey of exploration and wonder. If you've enjoyed this deep dive into the mysteries of black holes, don't forget to share your thoughts in the comments below. What fact surprised you the most? What questions do you still have about these cosmic giants? Let's keep the conversation going. And if you haven't already, be sure to like, subscribe, and hit the notification bell so you never miss out on our next cosmic adventure. Thanks for joining us on this journey through the wonders of the universe. Until next time, keep looking up and keep exploring.